Hello, this is the second part of a tutorial. In this video, I will go over a few basic commands in Python. While mostly I'll be focusing on a second tutorial file, this video is mostly for CLTs and faculties teaching calculus with Jupyter. I will show one of the future labs. I will show a few tips and tricks on how to teach it. And since most of our faculty is familiar with Maple, I will show as many connections to Maple as possible to ease the transition. The first thing we will look at is adding libraries. This is equivalent to Maple command with, where we can add libraries like students or plots. In Jupyter, we will mostly work with three libraries. One of them is NumPy. This is a mathematical library that contains most mathematical functions and is very good at computing and evaluating. Next one is SymPy. This is a symbolic mathematical library. Again, it contains most mathematical function, but it's very good at dealing with variables. Finally, we will also use matplotlib library, which is good at plotting. To add a library, we can use import. For example, to add NumPy library, I will say import NumPy, and we will also specify a shortcut for it as np. The reason for adding shortcuts is because multiple libraries may contain the same commands. For example, NumPy and SymPy, they both contain mathematical functions like square root. And we need to know which square root we are using, and therefore we will use np, or for SymPy we'll often use sp shortcuts to specify which root we are using. For example, here's the command, and notice I have np.sqrt4. That means I am using a square root function from NumPy library. Next, few comments about computation and NumPy. If I want to see a result of multiple computations and I type them in a single cell, as you can see, I will not see all of it. I can only see the result of the last computation. To avoid this, I can either use separate cells or we can use print command. Next, power. This is probably one of the bigger differences in terms of mathematical functions between Maple and Jupyter. If I want to find 2 to the power 5, instead of using a caret symbol, we use double asterisks. Finally, NumPy contains most of the mathematical functions, and to call them is pretty simple. All you have to do is type np dot and then the mathematical function. So for example, if I need cosine, I can say np dot cosine. If I need a constant pi, I can say np dot pi. Next part is about loops and indentation. There are a few different types of loops in both Maple and Jupyter. Here I will look at the for loop. For example, let's say I want to find a sum of numbers between 0 and 9. So the first thing I will do, I will set my initial summation to be 0. Then I have a for loop where a variable j will be in range 10. This means it will range between 0 and 10, not including 10, with a step of 1. Inside of the loop, we update our total by adding j, and then we show our result. This indentation here is important. It signifies what is inside of the loop. In Maple, while you can have them, they're not required because for loops have explicit end with the command and do. However, in Jupyter, you have to have them. If I skip this indentation, like in this example, as you can see, I will get an error. This error is because Jupyter now does not know what j is, since j was defined inside of the loop. Finally, we can also change our range. For example, if I write here range 10, 20, this means j will now be between 10 and 20, not including 20, with a step of 1. As you can see, my result will be 145. I can also add another digits here, 2. Now, this last digit signifies a step. So my j will range between 10 and 20, not including 20, with a step of 2. And so my result will be 70. Next, we will talk about arrays. Dealing with arrays in Jupyter is a bit easier than in Maple. There are a few ways of creating arrays. One is to use linspace. As you can see, it's part of a NumPy library. This particular command will create an array starting with 0, ending with 1, containing 100 equally spaced numbers. Another way is to use arrange. This is very similar to the range function from the for loop. It is also part of NumPy library, and in this case, this creates an array starting with 0, going all the way to 1, not including 1, with the step of point or 1. Finally, you can also create an array explicitly by telling which elements you want to have there using np.array. We can perform mathematical operations on arrays. For example, here is an array consisting of 0, 1, 2, 3, and 4. And what we are doing, we're taking the whole array and we are squaring it. What we'll do, it will square every element separately. So as you can see, the result is squares of every element. We can call a specific element of an array. So for example, here, s of 2 means it's a third element of an array. Keep in mind that Python is a programming language, so it will start indexing everything starting with 0. We can also use negative indices. -1 will stand for the last element of the array. -2, it will stand for second to last element of an array. There are other ways to get specific subarrays. You're encouraged to go through the rest of it on your own. Next, we will talk about plots. To plot a graph, we need to include a matplotlib.pyplot library. We will give it a shortcut plt. In some of the future videos, you may see me using %matplotlib notebook. We no longer will use this command, and therefore if you see it, you can ignore it. The way Jupyter plots graphs is it plots many points and then connects them with straight lines. Therefore, if you want to have a smooth graph, you have to plot many points very close to each other. To do this, we create a list. These are your inputs, in essence, the x coordinates. This is a list, in this case, from 0 to 5 with a step of point or 2. Then we will create a figure object. This is generally not needed if you're making something simple, but it is usually a good idea to get used to just always including it. Then we plot our function. So the command is plt.plot. First is the list of inputs, so the list of x coordinates, and then the list of outputs. In this case, I have a cosine of 2 pi t. The final thing here is the type of a line I want to draw. R in this case stands for red, so it will be a red color, and double dash means it will be a dashed line. In the future, you'll see we can specifically specify which colors we want to use and what type line we want to have in either explicit way or in a shortcut way like here. In fact, you can try to use other inputs here and see what you get. Finally, we use plt.show to display the figure. And this is our figure. As you can see, this is our cosine line. Uh, this is probably was the simplest graph. Here's an example of a more complicated graph. In this case, I will use linspace for our inputs. So we have numbers between 0 and 7. I will take 300 numbers equally spaced. I will do two graphs. One is the sine of x, the other one will be the cosine of x. Again, we're creating the figure. In this case, I will also specify the size of the figure. This is 8 by 6 in inches. Here are my two plots. So my sine will be red with a dashed line. We'll have a line thickness of 3, and I will give it a name because, as you will see later, we will use a legend for it. Second graph, the cosine will be blue. It will be a dotted line and not that thick. Y-limbs and X-limbs are range for your X and Y axes. Labels, X label and Y label. Then we have a title for the whole picture. We can add a grid. We can add a background color. We can add the legend, and the legend will have its own background color and a shadow effect. And then, of course, we will show the picture. So it will look much nicer. There are also ways of plotting multiple graphs in the same picture, like here. For that, we would need to use subplots. As you can see, there is also a variable here, AX, stands for axis. This will allow you to distinguish between multiple graphs on the same picture. This is more advanced. We will probably not use it. And generally, we will start with a much simpler graphs in the beginning. And as we progress through the semester, we will add more and more features to these graphs. And in this final part, we'll talk about functions. There are a few ways of defining functions. The more general one is using def. So in this case, I am defining function f that will have input x, and it will return sine of x. So for example, I can print f of a is 3 in this case, so we have the result. We can also input a whole list. So for example, here I have an array containing 1, 2, and 3. So I can evaluate a whole array, and so I have sine of 1, sine of 2, and sine of 3. If the function is pretty simple like this, we can also use something called lambda definition. So in this case, f is a function that has input x and output cosine of x. So as you can see, we can evaluate it as well. So this will be a cosine of 2. We can also create functions that are not just mathematical functions. For example, in this case, I have a function that will take an array and will give me the largest value of that array. So I will take a list L. It will set the maximum of it to be the first element of that array. Then going through the for loop, len of L is the size of the array. It will check using if-then statement here whether or not each element is bigger than the maximum. And the moment something is, the maximum will be changed. After it's done with the for loop, it will return the new maximum. So for example, if I have an array consisting of 0, 1, 2, and 3, maximum of that array will be 3. If I have an array starting with 1, ending with 10 with the step of 0.1, remember not including 10, then the largest value should be 9.9, and it is. There's a bit of an error here, and that's usually ignored. And finally, at the end of this video, I'll talk about structure of my labs. Each lab will consist of two files. One of them is the examples file. It will contain everything that is needed to do the actual assignment, and the file 2 will be the actual assignment. For example, this is the lab 1 examples. Everything is already solved. It will consist of multiple examples of how to solve the specific problem in many ways. Students need to read this whole file and try to understand how to do things. CLTs and faculties are strongly encouraged to do the same before the class. One of the worst things you can do is just run the code, show the students the result without explaining what each line is actually doing. And the second file consists of problems. Usually students will start with adding all the needed libraries, and then they have to answer all of the questions. Each question usually will consist of multiple sub-questions guiding students through the problem. To answer all of the questions, students first need to read the examples file to absorb all the information. Some of the questions will have a bolded answer. This is a markdown cell. Usually these questions also ask something specific, so the students have to answer in their own words. To do that, they can highlight the cell, double click on it, and then write their answer and finally run it.